So here's a new notation. This will be for what is called the power set of a given set. And here's all you need to know about the grammar is if you take a term, any term, so a variable, a constant, or something more complicated, and you put a fancy looking p with some parentheses around it, then overall you will have a term. And that's all you need to know about the grammar. How about the definition? So here's what it means. So this, which you read as the power set of x, so this is just how you read it in English, the power set of x, is how you would read this. That's defined to be, this is definition 36, by the way. It's defined to be the following set of things. So, like all the definitions of terms that I give you, I think all the ones I've given you so far, they all take this form of something with this notation, where you have curly braces and a bar. So that means I'm describing a set by giving you the condition for membership. That's the idea. So that means to make any use of this definition, you need axiom 5. Here comes the definition. What is the condition for membership? What does one have to do in order to be an element of this set? One has to be a subset of x. Let me write that nicer. And that's it. That's the condition for membership. So how would you read this? It is the set of things that are subsets of x. So in other words, it's the set of subsets of x. So that's the thing to remember. It's the set of subsets of x. That is what is meant by power set x. And here's the LaTeX for this symbol. People use different notations for this. This is a kind of common one. So to make the fancy p, you can do this. I don't know if you need some special packages for this to work. I mean, you just put a regular p here. You type this in LaTeX and that gives you the fancy p. And then you just put regular old parentheses like that. Yeah, so quick example. So imagine you have, let's do a example on its own page, just intuitive. So nothing to do with proofs, but it helps you imagine the right thing when you're thinking about power sets. So let's say you start with a bag that contains a flower, a square, and a smiley face. Then what's the power set? Well, it's the set of subsets of this thing. How many subsets can you think of? So here are some subsets. There's some that, well, there's one thing that's a subset of every given set. Actually, before I go on with this conversation, I would say pause the video here and think to yourself, count for yourself. How many subsets do you think this set has? So the set has 3 things. How many subsets can you think of? See if you can get them all. Okay, now I'm assuming you've done that, and let's do it. So here's one that people sometimes miss. Remember this fact, theorem 13, the minimality of the empty set? One component of it is it's telling us that the empty set is a subset of whatever you want. The empty set is always a subset of any given thing. So here's an empty bag that represents the empty set. This is one of the subsets of this thing. Okay, here's another kind of obvious one that might get forgotten if you don't think about it very clearly, is if I take a bag that is just a copy of this original bag. So, okay, so up here is my original set, and down here I'm trying to list as many subsets as I can. So if you take a bag that's just a copy of the original bag, then that also counts. So this idea came up very early on, right after we defined the idea of a subset. Right in theorem 7, part 1, this idea that the inclusion relation, this subset relation, is reflexive, meaning things do it with themselves. So everything is a subset of itself. So this original bag, a copy of the bag, is a subset of itself. All right, if you missed those two, then I would say pause the video and try again, see if you can get them all, and figure out how many there are. Okay, let's continue giving the answer. So there's the subsets that consist of just one of the things in there. So just a flower, or just the smiley face, or just the box. And these are singleton sets, right? This is singleton flower, singleton smiley face, singleton box. And then there are the doubletons. So the sets that you form by putting two things together, like flower box, or smiley face box, or flower smiley face. And that's it. So you get these 8 subsets. So what then is the power set of this thing? Thinking of this as being a term, what is the power set? This is an object. What is the power set of this thing? It's a bag, a set. If I follow this convention where I bag things up instead of putting them inside curly braces, it's a bag of bags. So it consists of all of these things. I don't know why my bags look like onions, but the idea is supposed to look like a sack, and then you've tied it up here or something. I don't know. But yeah, so the power set of a bag consisting of 3 elements is going to be a bag consisting of apparently 8 bags. Okay, so that's the intuitive idea. Of course, this does not help you prove anything. You cannot write a convincing proof with just this idea. You need, what I'm writing in yellow here, you need the definition. So somehow you have to use this with axiom 5 to make use of the idea of a power set. So let's look at proving things about power sets in the next video.